Okay, in this video we're going to dive into Chapter 4 and the remainder of Chapter 10, where we will begin to develop additional techniques for isolating specific parts of a circuit. So rather than solving for every voltage and current in a circuit, we're going to solve only for segments of the circuit that are important to us, and for simplifying the analysis in general. And all of this applies to linear circuits. So this is important because it's going to lead us to our first technique that I'm going to discuss here in a moment. A circuit is linear if and only if it satisfies additive and multiplicity properties. So first, let's explore the additive property of a circuit. And in doing so, I'm going to take this circuit segment shown here. I'm assuming this is a circuit. In other words, this is closed loop, and that's where the dots are going. So there's a circuit here that is not being drawn. So if we consider this segment, let's assume this resistor on the right has value R, current I going through that R, such that we have a voltage drop V across it. Okay, and so we can see that KCL at this node would tell us that I can be composed of contributions to the branch on the top, call that I1, and contribution to the branch on the bottom called I2. So we can write a KCL expression that I is the summation of I1 plus I2. Okay, so let's now express the potential V in terms of these currents. So we know that V equals the current I times R, and I can be re-expressed as I1 plus I2. Distributing the parentheses, we get I1 times R plus I2 times R, and we note that each of these terms are voltages, so we can rewrite this as voltage V1 plus the voltage V2. So the question is, what are voltages V1 and V2? Well, we could describe voltage V1 as being the voltage dropped across R that is due to the current coming through this top path alone. And we can describe the voltage V2 as being the voltage dropped across R due to the current through the bottom branch acting alone. Okay, so let's explore the multiplicity property as it pertains to circuits. So let's just assume we have a resistor being driven by a single voltage source of value V, such that current I will be drawn from the voltage source and go through the resistor. Okay, so in this case, you simply have the relationship that the voltage across the resistor, V, is given as I times R. So if we consider a similar circuit, a single voltage source driving the same resistor R, but we apply now voltage K times V, what is our expected result? I'll call this I star. We can see that I star is going to be the voltage across the resistor, which in this case is KV over R. It can be rewritten as K times V over R. Noting that over here, I is V over R, we can see that the V over R terms is the same, so this can be rewritten as I star equals K times I, which is the original current. In other words, in order to find I star on the circuit on the right, we don't need to necessarily resolve the problem. We note that the voltage source driving the resistor is just multiplied by K in part 2, and the resulting output current will likewise be multiplied by term K. So it's just a scaled version of the original. So these properties of linear circuits leads us to the principle of superposition, where that's defined as the output voltage or current, so the voltage across an element or current through an element, can be determined by taking the summation of the individual voltages or currents due to each independent source acting alone. So the method is as follows. First, we're going to set each independent source, or all independent sources, I should say. Set all independent sources to either 0 volts or 0 amps, depending on the source, except of course of one or a group of sources. So we have to always leave at least one active, or at least one group of them active. You don't have to do just one source at a time, except for one or one group. In other words, we're just turning off sources. So if we have a voltage source that is 0 volts, that looks like simply a short circuit. In other words, the voltage between points A and B in the circuit are 0. In other words, that will be replaced by a wire. And if we have a current source that we turn to 0 amps, that's like creating an open circuit. Second, we're going to solve for the output voltages and currents under the scenario that we have a single source or a group of sources activated. 3, we're going to repeat steps 1 and 2 for each group of independent sources acting alone. And then finally, we're going to sum the results for each source acting alone, or each group of sources acting alone. And one final note, dependent sources must remain on. This is very important. We can't deactivate a dependent source in the problem. Dependent sources constrain the relationship between nodes, like any other passive element constrains the relationship between nodes. And if we remove that constraint, we could jeopardize our analysis, and will most likely change the functionality of our circuit. So we cannot do that. We keep dependent sources active. Okay, let's do an example. We're going to solve for currents I1 through I4 in this circuit using the principle of superposition. Note, I might ask this question as, for example, solve for the portion of I1 or the contribution to current I1 due to the 120 volt source acting alone. That's just a rephrasing of the problem. I might use superposition to understand the contribution to some specific parameter inside my circuit due to a certain source or a certain set of sources. Maybe to understand how much of the voltage or current is being distributed amongst the circuit and where it's coming from. Okay. So first thing we're going to need to do is redraw the circuit for each individual source acting alone. So let's take the 120 volt source first. So I'm going to redraw the circuit with the 120 volt source active. Okay, so note, when we get to the current source, we're setting that to 0 amps, so that's like creating an open circuit. Now in this circuit, we don't have I1 through I4 anymore, we have some portion of I1 through I4. So I'm going to call it I1 star, I2 star, I3 star, and I4 star. Okay, so in this problem, I'm going to use nodal analysis to solve it. So I notice that I have 1, 2, 3 essential nodes, so I'm going to create the bottom one to be my ground, which pins this potential to be 120 volts. This node becomes, call it Vx, and that's my, I only have 2 essential nodes, so Vx and where I have my ground. So I need 1 KCL to solve the problem, so I'm going to do a KCL at node Vx, and the current through the 6 ohm resistor is given as Vx minus 120 over 6. The current through the 3 ohm resistor is Vx minus 0 over 3. The current through the 2 ohm and 4 ohm series path is given as Vx minus 0 over 6 ohms, and all that must equal 0. So solving this single equation, you get that the voltage Vx is going to be 30 volts. And then finally, noting that we can use that potential to solve for I1, I2, I3, and I4 star. And you get the following answer. I1 star is 15 amps. Note that I1 star could be expressed in terms of the nodal voltage Vx as being 120 minus Vx over 6 based on the direction that we drew that current. That is opposite of the parameter that I get in this equation, because when I expressed my KCL equation, I assumed all my currents were exiting. Likewise, I2 star can be expressed as Vx over 3, I3 star and I4 star are equal to each other because they're in a series path, and that's given as Vx over 6. Okay, part 2 of the problem is we have to consider the 12 amp source active and the voltage source is set to 0 volts. So if we redraw that equivalent circuit, we have the right part, and we've shorted the voltage source because we've set it to 0 volts. Now we're solving for I1 double star, I2, I3, and I4 double star. In this problem we have 1, 2, 3 essential nodes, so we're going to need 2 KCLs. I'm again going to set the bottom to be ground. Call this node Vx, this node Vy. So first my KCL at node Vx. The current through the 6 ohm resistor is Vx minus 0 over 6. The current through the 3 ohm resistor is Vx minus 0 over 3. And the current through the 2 ohm resistor is Vx minus Vy over 2. Set it equal to 0. Next, KCL at Vy. First, the current through the 2 ohm resistor, Vy minus Vx over 2. The current through the 4 ohm resistor is Vy minus 0 over 4. And there's a 12 amp current coming out of that node, so plus 12. That must equal 0. Okay, so based on the solving for Vx and Vy, we once again can find the individual currents I1, I2, I3, and I4 for only the 12 volt activated at a time. And then finally, we can find the final values for I1, I2, I3, and I4 by summing the individual responses to each source. That's single star and double star. And we'll end up with I1 equal to 17 amps, I2 equal to 6 amps, I3 equal to 11 amps, and I4 equal to negative 1 amp. Now, one good method to practice nodal and mesh analysis is to, again, take the original circuit, solve it using nodal or mesh analysis, make sure you can get this solution that shown on the bottom here. And practice again using superposition to make sure you can get the individual responses of each source and note the summation. Try these again with mesh analysis or any other method that you can conceive. And on a final note, I wanted to mention a much quicker way to apply the principle of superposition. So let's consider the original circuit again. This time I'm just going to write my KCL expressions like I would normally do in solving the circuit using nodal analysis. Note I chose my bottom node to be ground, so that makes this node 120, Vx, Vy. But when solving this, instead of applying the actual values for the current source and the voltage, what I'm going to do is make those variables, Vs and Is, when I write my expressions. So note the first term is the current through the 6 ohm is Vx minus Vs over 6. And likewise, I do that for the current I. And then, in order to find the individual contributions to the sources, instead of solving the circuit with plugging both values for Vs and Is in, I'm going to solve the systems twice. And the first time, I'm going to set Vs equal to 120 and Is equal to 0. And I get the solution that I got with solving the problem in superposition using the first method. In part 2, I'm going to flip that and set Vs equal to 0 and Is equal to 12 and resolve the problem. This will save you a lot of time in constructing and redrawing circuits, as well as applying them using mathematics to solve the problem.